This is a video from section 12.4 and it's based off the lecture notes. Recall, the determinant of the 2 by 2 matrix A, B, C, D is equal to A times D minus B times C. For example, suppose I want the determinant of 2, 4, 7, 9. Well, this is 2 times 9 minus 4 times 7. 2 times 9 is 18. 4 times 7 is 28. 18 minus 28 is negative 10. Okay? Now, let's take the determinant of the 3 by 3 matrix A1, A2, A3, B1, B2, B3, C1, C2, C3, and we're going to expand around the first row, and we're going to do that the whole time. Okay? Now, I'm going to take the first entry, which is A1, and I'm going to multiply it by the determinant of the 2 by 2 matrix B2, B3, C2, C3. And that matrix is found by eliminating the row and the column that contains the entry A1. And so you can see that this submatrix is what's left. Then I'm going to go minus A2, that's this entry right here. I'm going to eliminate the row and the column that contains the entry A2, and I'm going to multiply by the determinant of the submatrix B1, B3, C1, C3. And then following along that pattern, I'm going to add A3 and multiply by the determinant of the submatrix B1, B2, C1, C2, and that's found by eliminating the row and the column that contains A3. So you can see I'm just looking at this piece right here for that last term. Now, let A equal the vector A1i plus A2j plus A3k. Or you can call A, A1, A2, A3. And then B is the vector B1i plus B2j plus B3k. Or you can call it B1, B2, B3. We will define the cross product of A and B written A cross B as follows. So A cross B is going to be the indeterminate notation, I should say. The first row will contain the vectors I, j, and k. Those are the basis vectors for R3. Okay? The second row will contain the components of A. So in other words, the second row will be A1, A2, A3. The third row will be B1, B2, B3. So I'm going to take I, and I'm going to eliminate the row and the column that contains I, and I'm going to multiply by the determinant of that 2 by 2 submatrix, which in this case is A2, A3, B2, B3. Then I'm going to go minus J times the determinant of that submatrix found by eliminating the row and the column that contains J, which in this case will be A1, A3, B1, B3, the determinant of that, again, of that submatrix. And then I'm going to add K. I'm going to eliminate the row and the column that contains the K, and I'm going to multiply by the determinant of A1, A2, B1, B2. And the important thing about this is when you take the cross product of A and B, you're going to get a vector back. Okay? Now, with that in mind, let's take a look at an example. Suppose A is the vector 4, 3, negative 2. Suppose B is the vector 2, negative 1, 1. And I want to take the cross product of A and B. So we're going to use determinant notation to get there. So in the first row, we have ijk. In the second row, we have the components of A, which in this case will be 4, 3, negative 2. And in the third row, we have the components of B, which would be 2, negative 1, 1. Now, let's take I. I'm going to eliminate the row in the column that contains the I. And I'm going to multiply by the determinant of the submatrix found, which is 3, negative 2, negative 1, 1. So notice how, again, I eliminate the row in the column that contains the I, and I'm going to multiply by the determinant of this 2 by 2 submatrix. And then I'm going to go minus j, and if you don't mind, I put the j over here, and I'm going to multiply by the determinant of the matrix found by eliminating the row and the column that contain the j, which in this case, it'll be the determinant of 4, negative 2, 2, 1. And then I'm going to add k times the determinant of the submatrix found by eliminating the row in the column that contains the k, which in this case, I'm going to multiply by the determinant of 4, 3, 2, negative 1. And this is a vector, you guys. Okay, so again, when you take the cross product of A and B, you will get a vector back. So when I am all done, I get 1i minus 8j minus 10k. So therefore, A cross B is 1i minus 8j minus 10k, or A cross B can be written as 1, negative 8, negative 10 in this form. Okay, so there's two different ways to express a vector. What you don't want to do is write A cross B is I minus 8j minus 10k within these brackets. So that here, if you write it this way, that just means you're mixing up two different notations. Now, I want you to notice something. If I take the cross product of A and B, which is 1, negative 8, negative 10, and I dot it with 4, 3, negative 2, I get 0. And so what that told me was A cross B is orthogonal or perpendicular to A. And if I take the cross product of A and B, which again is 1, negative 8, negative 10, and I dot it with 2, negative 1, 1, I also get 0. And so A cross B is orthogonal to B. So when you take the cross product of A and B, what you did is you found a vector that is perpendicular to both A and B. And that will be a theorem that I will address shortly. Now, in example 2, suppose A is the vector t cosine t sine t. So I want you to be exposed to both notations, okay? And B is the vector 1, negative sine t cosine t. And I want the cross product of A and B. So in the first row, we have ijk. In the second row, we have t cosine t sine t. In the third row, we have 1, negative sine t cosine t. Now, when we expand this out, we get 1i minus, in parentheses, we have t cosine t minus sine t, j, plus negative t sine t minus cosine t, k. So how did I get the 1? Don't forget, cosine t times cosine t is cosine squared t. And then I'm going to go minus a negative sine squared t. So I'm getting cosine squared t minus negative sine squared t. But that's cosine squared t plus sine squared t. And that's just 1. So that's where that 1 came from. And then the rest should be pretty straightforward. I took the main diagonal, t cosine t, multiplied those entries, and then I subtracted 1 sine t. That's for the second component. And then the third component, I took negative t sine t minus 1 times cosine t. And that's example 2. Example 3. Suppose A is the vector 2, 3, 4, and I want A cross 2A. So in the first row, we have ijk. In the second row, we have 2, 3, 4. And in the third row, I'm just going to double each of the components. And so I have 4, 6, 8. So again, I want to get you guys used to different notations. So in the first component, I'm going to get the vector 3, 4, I'm going to get the number found by taking the determinant of 3, 4, 6, 8, right? How did I get that? So remember, that's the first component. So I take the I and I eliminate the row and the column that contains the I, and I'm taking the determinant of this submatrix. That's how I'm getting that first component. For the second component, I'm going to take the opposite of the submatrix found by eliminating, let me say it again. I'm going to take the determinant of the submatrix found by eliminating the row in the column that contains the J, right? So I'm going to take the determinant of 2, 4, 4, 8, but I'm going to take the opposite sign because you're in the second component. And then for the third component, I'm going to eliminate the row in the column that contains the K, and I'm going to take the determinant of the submatrix found accordingly, right? Which in this case is 2, 3, 4, 6. And if you notice, I get 0, 0, 0. And so the answer is going to be the 0 vector. So if you notice, if one row is a scalar multiple of another row, and you take the cross product of those two vectors, you're going to get the 0 vector the whole time. Theorem. It turns out that the vector A cross B is orthogonal to both A and B. So what I did was I wrote down the definition of A cross B. The first component will be A2B3 minus A3B2. The second component will be the opposite of A1B3 minus A3B1. The third component will be A1B2 minus A2B1. And I want to show A cross B is orthogonal to A. So to do that, I must show that the dot product of A cross B with A ends up being 0, and that's a scalar. Remember, when you take the dot product of two vectors, you must get a scalar back. And so I took A cross B dot A, and that's equal to A2B3. So essentially, the vector A2B3 minus A3B2, that's the first component. Then I took the second component, which is the opposite of A1B3 minus A3B1. And then I took the third component, which is A1B2 minus A2B1. And then I dotted it with A, which is A1, A2, A3. So I'm going to take A1, and I'm going to multiply by this first component. And then I'm going to go minus A2 times the second component. And then I'm going to take A3 times the third component. And that's exactly what I did on this line. And then I distributed the A1 inside the parentheses. Distribute the A2 inside, distribute the A3 inside. And so it's straight algebra. And so this is A1, A2, B3 minus A1, A3, B2 minus A1, A2, B3 plus A2, A3, B1 plus A1, A3, B2 minus A2, A3, B1. Now, watch what happens here. We get to cancel a bunch of stuff. Notice how A1, A2, B3 cancels A1, A2, B3. And then if I take this term, A1, A3, B2, but the opposite, that's going to cancel this term. And if you notice, these two terms cancel. And I get 0. And so therefore, A cross B dotted with A is equal to 0. I hope that makes sense. And by a similar argument, we can show that A cross B is orthogonal to B. So it's a very similar computation. And that'll do it for this video. This is a video on section 12.4, and this is part 2, and it's based off the lecture notes. Okay, thank you.